Yeah, we can see the screen.
Can you see the screen? It's full screen now.
Yeah.
Okay, thank you. So thanks again, Joe, for the kind introduction. Thanks to Nigel and the organizing committee for inviting me to this special event. I know you probably have had quite a busy day already, so I'll try to keep it relatively light. And in this talk, I'm bringing together two disciplines, which I think are getting more and more connected now. And it's your generation who I think is going to master it even more than at present, and that's cosmology, understanding the universe, what's the universe made of, and so on, and artificial intelligence, which is becoming a very important tool, given the vast amount of data that are coming together. So I'm going to show you a few examples of that. In fact, already on that picture, just to whet your appetite, you see a map of dark matter, or at least what we think is a map of dark matter, using an effect called gravitational lensing. And on the left is something I'm going to mention as well, which is the future collision of our galaxy, the Milky Way and Andromeda. So these are two of the examples you're going to see. Now, before, just to explain, just to explain, I mean, we seem to live really in some kind of parallel universes these days. So it's difficult to tell when someone is giving a talk, it's impossible to tell where the person actually is. So I'm going to reveal where I am. So to put things in context, my work is at University College London. My residency is actually in Canterbury, not far away from the University of Kent. But actually right now, for family reasons, I'm actually in Tiberias, Israel, and which is a very ancient Roman town, 2,000 years old. And in fact, by the Sea of Galilee, and I saw two pictures I've taken just to show you where I am. It's the Sea of Galilee, and on the right you see the Mount Hermon, covered with snow. The tower on the left is a bit leaning. You might be able to spot that. But actually, I'm also, just to complicate things and about these parallel universes, I'm actually on a sabbatical right now, but virtually in Oxford, in All Souls College, Oxford. So these are my four different connections right now, four different universes, before we talk about the big universe. This is the outline of the talk. So there are four parts to this talk. I'm going to describe galaxy surveys in the context of cosmology. I'm going to tell you the current status of cold dark matter and the cosmological constant, and then to connect it, as I've already said, to artificial intelligence, machine learning in cosmology. And finally, and I think it's quite appropriate for this forum, to talk to you a bit about the training of the next generation in data science, and to give a particular example on a particular program we have at UCL. It was mentioned that I gave recently this George Darwin lecture, The Royal Astronomical Society. So this is a version, an upgraded version of that, an improved version, I should say, of that talk. So in terms of putting things in context, so you can see the wood for the trees, I'm trying to connect three elements here. Bottom left are the laws of physics, right? There are laws of physics which we would like to think, it's maybe debatable that they exist even if we as humans don't exist. Then there is all this human knowledge which was accumulated over hundreds and thousands of years. And now we have this new kid on the block, artificial intelligence. And the point I want to make is those three should be connected. So I'm actually not among those who believe that we don't need any more humans and we just let AI do everything for us. I think it's this connection which is important. And in fact, I like the concept of rather than AI being artificial intelligence, to actually be augmented intelligence. So what does that mean? It's really about having the cognitive technology is designed to enhance human intelligence rather than replacing it. So that's the idea. And it reinforces the role human intelligence plays when using machine learning and deep learning algorithms to discover relationships and solve problems. Before we talk about the nitty-gritty details, just to say, I know most of you are on the third or fourth year of your studies, so you probably heard about dark energy, which is some kind of new incarnation of Einstein's cosmological constant. So Einstein introduced it back in 1917 in this paper written in German, but you can find the English translation online. And he advocated adding this Greek letter lambda to his equations, which we'll see later. His reason was different. He wanted to produce a static universe with particular value. It turned out the universe was expanding. He thought it was his biggest mistake, the biggest blunder of his life. But now we think there is lambda or something like that. And what it does, it's causing in recent times an accelerated expansion of the universe. So we've known for over 100 years the universe is expanding, but now we know it is accelerating. So that's the basic picture. And at the present universe, about 70% are made of this dark energy, and which we don't quite understand. It's very elusive. And 26% of dark matter, which is also mysterious, and only 5% of baryons. The stuff we're made of is only 5%. We belong to a minority. And now to the data. So this dark energy has caused people a lot of headache, but also challenges. Could we do better and figure out what's going on? So this has led to many projects which are very demanding. And don't worry, not remember all these names, but this dark energy survey, which I'll talk about, DESI, Rubin, LSST, Euclid, Space Mission, SKA. Most of these are actually in the process of being constructed. You can see how the data goes up. So in dark energy survey, which we're talking about 1 terabytes per night, and in LSST it's going to be 15 terabytes, and in SKA, a radio survey is 1 petabytes. You can see the number of galaxies goes up from 300 million here to billions, and so is the cost, which goes from tens of millions of dollars to billions. When we try to convince the funding agencies to give us money, we like to say that it's only $1 per galaxy, right? If you have billion galaxies, it's $1 billion, it's only $1 per galaxy. I don't know if they buy this argument, but I like it. It's kind of shows that it's good value for money. And maybe perhaps a comment about sociology, like in particle physics, we work now in very big teams. When I was, doing my PhD back in Cambridge, perhaps, we worked in a team of a few people, and then we went to a project called 2DF with 30, and now in DES we're 400, and in this other project, number exceeds 1,000. So it's another thing to bear in mind when you join projects like this. You'll be talking to many, many people, which of course is very exciting in some ways, but you also have to, learn how to communicate and do it efficiently. That's kind of these are just pictures of what's going on in this survey. So I mentioned dark energy survey. You'll hear more about it. DESI, these are on existing telescopes. This one is in Chile. This is in Arizona. This is LSST, now named after an astronomer, Vera Rubin, which is on the next hill, just next to DES, being constructed. And this is the European Space Agency mission Euclid, which is currently under construction as well. This is a CCD array, and this is some of the lenses for DESI, for example. that were actually assembled in our basement at UCL. There are many, many projects, and one could spend many hours on those projects, but I should give you kind of a bit of picture of the dark energy survey, because I've been involved in it almost from the beginning of this project. And now we can see the fruits. So it takes a multi-probe approach of looking at the sky and counting not only galaxies, but classes of galaxies, looking at the large-scale structure of the distribution of the galaxies, and also using weak gravitational lensing, and in a time domain, supernovae. So some of you may not have heard about before. I'll give a brief summary how these things work. Luckily, already in 2019, well before the COVID disaster, we managed to finish all the observations. So all the data, 300 million galaxies are in the bag, and also thousands of supernovae, and there are 400 scientists in 7 countries still busy analyzing the data. So it's one thing to collect the data, another thing to analyze it. And but already 250 papers, and also the data, most of the data already public. So any of you can download data and do science with it. It's public. This is a commitment to the funding agencies. This is what the telescope looks like, and this is the camera. As I said, partially built at UCL, but also in some other parts of the world. It has the same principles as a camera on your iPhone, except that it costs $40 million and it weighs several tons. Now, it's a long journey, as I said. So some years ago, we decided that it's good to document it in a book. And this is this dark energy survey book. I don't know if you can see it, but I'm actually holding here also a real hard copy. It was very nice to actually receive it. Despite the pandemic, we managed to finish it, or maybe I could even say maybe I had more time, thanks to the pandemic, to actually finish it. And this appeared on September. You can see it on the World Scientific website and also on Amazon. And it tells the story of how it's all happened, building it, and the main dark energy science, non-dark energy science, and also some reflections by a philosopher, an anthropologist, a poet, and an artist. So we're trying to look at it in a bigger picture. You know, if you're interested, you're welcome to look at it. There's some chapters online for free as well. So this is this dark energy survey story. Now, what is it that has given this motivation to thousands of scientists around the world to spend many, many years in this problem, and also to funding agencies, taxpayer, essentially to give us all this money to do it? So I already mentioned Einstein adding a constant to his equation. So this is this lambda. On the left-hand side, note, on the left-hand side, all these R, some of you already had perhaps a general relativity course. So this R, we won't go into details, but it represents curvature of space-time. And he put this lambda there. So initially there was no lambda, but then he added it in 1917. General relativity is from 1915. So 2 years later, he added it. And on the right-hand side, this T mu nu stands for the contents of the matter and energy contents of the universe. So depending on what they are, for example, dark matter, dark energy, and so on, and baryonic matter, this is the kind of source term, and it would tell space-time how to curve. It's one way of thinking about it. One can also put this lambda on the right-hand side, and then it has a meaning not of a tweak to the curvature, but rather as an addition of some energy. And the particle physicists tell us this should be some sort of vacuum energy. And that's the current popular interpretation of this lambda, that it's some sort of vacuum energy. Now, I told you that Einstein put it there, and then he decided that it was wrong to put it. He said it should be 0. So how come I mention it again? Because he looked at a particular value to give a static universe, Now, but it's a free parameter, so it could be, you can have any number you want. And we think from observations that now it's actually there, but with a value that gives us an accelerating universe. Okay, so that's the basic concept. Now, you can take the weak field limit. After all, general relativity should agree with Newtonian physics. So if you do that, you find something which you're probably more familiar with, that acceleration is minus gm over r squared. This is Newton's famous law. But now there is an extra bit, which is lambda over 3r, which you can see if lambda is positive is opposing to the gravity 1 over r squared is attractive, and this is a repulsive force, okay? So if you like to think of it intuitively, that's the way to think about it. In fact, something which really impressed me some years ago, we even wrote a little article about it, that Isaac Newton in Principia also hypothesized that there is such a law. Okay, but then he realized that it's completely unimportant in the solar system. You heard talks, I believe, by Nigel and others about planetary systems. Their lambda is not important, but the moment you move to separations between galaxies, including us Andromeda, it starts playing a role. Lambda, Einstein didn't like it, but his good friend Eddington, a Cambridge professor here, just sitting in Cambridge on a sunny day, he actually liked lambda and even called it "I'm a detective in a search for a criminal." So you can see this subject has always been kind of confusing conceptually. I've made a little drawing here to show, I want to emphasize that the way we think of it now is in terms of an equation of state. It's something which probably you've seen in one of your courses. It's pressure to density times speed of light squared. And if you do the mathematics, you find that the density goes like the scale factor of the universe, the amount by which it expands. So A was very small at the beginning. We like to normalize V1 at present. And you can easily see that when this W is 0, we get rho goes like a to the minus 3. And that's essentially the red curve here. Okay, so the density, this is high redshift, earlier times, the universe expands, the density gets diluted, okay? But if W is minus 1, you can see the energy remains constant. So in earlier times, dark energy was not important, matter dominated, but the universe started accelerating at about 6 gigayears ago, and it became dark energy, or rather the equality between dark matter, dark energy happened about 3.5 years ago. And now we have more dark energy, I said about 70%. So it's an evolving universe, and it's interesting that it started accelerating and then became with those equal quantities in those epochs. For reference, the solar system is about 4.5 gigayears old. Okay, so how do we do it? What does the trick? I mean, how do we actually know that there's dark energy? So obviously we don't just look at the sky and see dark energy. It's what's called an indirect measurement or an inverse problem. So a famous way to do it is to use standard candles that nature has kindly provided us with. So if you have a factory of candles and they're all produced to produce the same amount of light, obviously the further one is, the less flux you get, and you can tell the distance. Okay, if a candle is 3 times further away, you'll see 1/9 of the flux, and we can use that to measure exactly that space curvature, space-time curvature that appears in Einstein's equation. This is very common, a very great technique, and the two teams that used it in the late 90s won the Nobel Prize for that discovery. Using those standard candles, they discovered that the universe is accelerating. Similarly, one can use those standard rulers which you can place on galaxies and the CMB. You can do the same thing. Then there's the technique of clusters of galaxies. You count how many massive clusters are there. This is one of them from Hubble Space Telescope. But also you see that some objects are distorted. That's because of this effect, also hypothesized by Einstein, of gravitational lensing. We see it also on the right, something which is maybe a circle gets distorted through the intervening matter and looks a bit, it may have like a banana shape or something like that. So that distortion, we can work it backward and learn about the stuff between in the universe and therefore the contents of the universe. We do it from the expansion of the universe and the growth of structure. Structure grows as the universe expands. Let's see if this animation will work. It doesn't seem to work to the PowerPoint. Never mind, not to worry. But oh, maybe. Oh yeah, good, it's working. Okay, so you should be able to see that regions which are overdense becomes even denser. The rich gets richer. Regions which are underdense becomes more empty. So that's the lesson to take here. And this growth also depends on dark energy, dark matter. So through the growth of structure, you can also learn on the contents. Okay. So all these techniques have led us to believe that indeed there is some sort of dark energy. So this is this W. So okay, so what you do, you measure the flux you measure from supernovae against the redshift, and you can see these are orange and red are two different samples. And the key point is that this model, the blue, which was very popular when I was a student, when I did my PhD in Cambridge, it was believed that lambda is 0. Okay, it was believed that lambda is 0, and that's that model. So that model is no longer correct. And now we believe it's a universe which has about 30% dark matter, 70%. Sorry, this 0.3 is dark matter plus baryons, 30%, 7% dark energy. And this W is very, very close to -1, which gives us cosmological constant. So we still have, it's 218 plus -5%. We still have colleagues who think maybe it's more complicated than that, and it's not just a constant. Time will say. I'll run through this one very quickly. This is using some other techniques I mentioned, clustering, weak lensing, and again, number to take home, it's about -1. In this case, it even gave -1.00, but this is from the early results, and we are eagerly waiting for the new results. I should say that not everything is so perfect in this model. And for example, the Hubble constant, which measures the expansion rate of the universe, is a bit controversial at the moment. We call it tensions. And according to one technique, it's 74. Another technique, it's 67. You may think, what's the big deal? Well, it's a big deal. It's a big difference. And it affects all kinds of results. So we're trying to find new techniques. You might have heard about gravitational waves. There are now 50 examples of colliding objects, like two black holes or a black hole and neutron star or two neutron stars. This is an amazing measurement, also confirming Einstein theory. And we can use that to also tell the Hubble constant, and this is work from a former student of mine, Antonella Palmassi, and you can see probability for Hubble constant against Hubble constant. You can see two techniques that disagree, the blue ones. That's a new technique with gravitational waves, but it's still preliminary. Sorry, both the gray and the red are techniques using gravitational waves. You see, they're so big, so they're still friends with those two other groups because they are so big, but it's something to look forward to. It's a growth area I mentioned because those of you who may move into PhD programs, this is a very good topic, gravitational waves. It's nice because it brings together not only cosmology, but also stellar astrophysics. Now, at this point, I'm turning into the AI part of it. So you can see that there are big conceptual problems, okay? You can also see that there are lots of data and thousands of people working on it. But we need help because these are huge data sets. I talked about billions of objects. But even to get to those objects, you have to analyze images. And this is very, very complicated. Luckily, computer science, there's been a lot of progress in computer science now. And we can actually use that. But we have to ask questions, are these only black boxes, this AI, machine learning? Can we actually explain, interpret them? What if we don't have the proper training set? If you teach a computer that there are only cats in the world, no dogs, and then you show them a picture of a dog, would it know that it's something different than a cat? And how do we include prior physics? How do we learn new physics? These are interesting questions, and those of you who have done a course in statistics must have seen Bayes' theorem, which we use quite commonly in traditional statistics, but also we're trying to relate it to the AI. Now, usually the argument for why AI, which I already I've articulated myself, is that because there are lots of data, we wouldn't like a student to spend 3 years just looking at images. We let the machine do it. But at this point, I also want to show you in a critical way that, in fact, the human brain has limitations. What you see here is not an animation. It's not an animation. It's just a static picture, but there are actually 12 black dots in this diagram. And I have not met any human, because I showed it in various lectures to my students and so on. I have not met any human who could see 12 black dots all at once. So the human brain has its own confusion. So, we would like also the computer to help us with that. There are many techniques now which are available, which can be just downloaded freely. One is called scikit-learn. That one is called TensorFlow. I won't go into details, but I want to just say that those of you who like computing and so on, there's a lot out there, and also with examples. There are also excellent textbooks. It's much easier now to get into it than in the early 90s when I started playing with it. We had to write every code. It's much easier. So this has entered our field, and there are basic things, right? You image the sky. You want to know what's a star, what's a galaxy. You wish to know what's a supernova of a particular type, so you can do the cosmology I've described. And I mentioned the gravitational lensing. I'll show in a moment measuring distances to galaxies or redshifts, how to measure masses of galaxies, and also to search. It's not unrelated to planets and exoplanets, because after all, it's the same imaging. Sometimes you can use the same imaging to study those, and I already mentioned gravitational waves. So it's just a shopping list to convince you how useful those techniques are. I just mentioned that I myself got interested in it back in the early 90s when it was really on the fringes. But at the time, we sent images to 6 living gurus, asked them to classify them, and then we reproduced it, right? So we could show parameters of that galaxy to a computer, and based on what they learned from the expert, they could classify it. And if we only classify galaxies into their main types, which are elliptical, sparse, and stars, you can see it's 90-something%. So now it's very common. Photometric redshift is how to get a redshift to a galaxy. Ideally, you'd like to put a spectrograph and get spectral lines, and then you can tell the redshift. But with some techniques, we only look at the sky using imaging in 4 or 5 bands, like this one. In this case, you see 4 bands called GRIZ. This is wavelength. And this is a spectrum of a galaxy, the same spectrum that's flux against wavelength. That's spectrum. You've learned that in your classes. If you put it to different redshifts, you'll see obviously different amount of light through the filter. So you can do the reverse, and from the amount of light or flux in each filter, you can tell the redshift. And back then, it's now quite a long time ago, we devised an artificial neural network where you feed in those measurements and train it on galaxies where you know the true redshift, and then can predict the redshift. Okay, so this turned out to be quite a useful method. A student of mine, Sunil Mukesh, together with postdocs Antonella Palmasi and Will Hartley, have extended it now. This is a paper from December, to actually also tell us not only the redshift, which is that distribution, but also the amount of stellar mass. Okay, so you can see how these things could be very useful, because the stellar mass can tell you more about the properties of the galaxies. But this was the earlier approach, and now we actually there's a new technique called deep learning. So what's deep learning? If you have not seen it before, I would say it's a subset of machine learning. It's a subset of machine learning, and which by itself is a subset of artificial intelligence. So what is it? It's in the old days when we classified galaxies, for example, you take an image of that object and you characterize it. You run a separate algorithm to deduce that this object has two circles here, and those features, and maybe has a particular size and height, and that's what you feed in. These are called, it's called feature extraction. And then you put it there, and this machine, based on training, tell you whether it's a car or not a car. The new technique is called deep learning. You feed in the whole image. The whole image. You don't have to do this pre-selection of features. You feed in the whole image, and then it tells you whether it's a car or not. And you can see in astronomy now, there are many, this is just, I looked up the number of papers with deep learning in the title, and it's you see how it's growing. In fact, I checked it, but I haven't fixed the slide. In 2020, it's 90 papers, okay? So every few days, someone writes a paper with deep learning in the title, just in astronomy. Of course, deep learning came to us from particle physics. So what is the magic here? The magic here is you take an image and you convolve it with some filters. Now, there's the whole art, which filters you use, but you can imagine if you have many different filters, you can pick up features here. So it replaces the traditional feature extraction with less prejudice, because I don't say from the beginning, oh, I think there might be something which looks like a circle because I know animals have eyes. Here, I don't even know it's an animal. I just do those techniques of convolving it. That's what is fed. And then hopefully, if it works, and usually it works, it will tell you whether it's a bird, sunset, dog, or a cat. And now you can imagine with a project like LSST, the one named now after Vera Rubin, a famous astronomer who discovered dark matter in galaxies and so on. It's named after her. With LSST, we'll have about 20 billion galaxies, and someone has then to identify which of them will have arcs around them due to this effect called gravitational lensing, which I mentioned already earlier. This is a simulation because that's how we learn about these things before we do it on real data. Obviously, you can see here beautiful arcs. Some of them, however, are more difficult to find. But even then, I think none of you would like to spend years to look and find 1 million of those objects, while a deep learning algorithm managed to find it quite easily with about 90% success rate. You can also do deblending if you have situations that two galaxies overlap. How do you spread them? How do you split them into two? Again, you can use this technique of convolutional neural networks. I have to say that's a bit technical. This work by a former PhD student of mine who just recently started a postdoc in Poland. And this is also a problem of how to quantify not just individual galaxies, but the distribution of galaxies. This simulation each dot here is a galaxy in a simulation which is quite realistic. And here is another simulation which is very different, unrealistic. And by eye, you can see that they're different. However, when we use a technique called correlation function, which most cosmologists use, you can see that actually this statistic is not very sensitive to the structure we see, and it gives the same answer. So you need, we think, a better statistic. And this is one of them called minimum spanning tree, where you cannot connect the dots. It's a nice mathematical approach already proposed previously. And you can see histograms of properties which tell you about this tree. I don't have time to explain details, but there are 4 properties. And you can see that now the blue and green are more easy. It's easier to discriminate one against the other. Okay. And finally, we can also use these techniques to derive maps of dark matter. There was one on the very first slide. That's another one from the Dark Energy Survey. Red means high density, like a mountain in density field, and blue is an underdense region, like a valley. This is supposed to be dark matter, if we got it right. Of course, computer-generated dark matter. You can then look for galaxies on top, and you see that they're there. And you can see that there's some correspondence. Dense regions have more galaxies, empty regions have fewer galaxies. And here, again, Niall Jeffrey, my former student, is producing something which is preliminary. Very, very soon, you will see the actual results. But essentially, this is using lots of data from Dark Energy Survey to get a dark matter map. This is, by the way, only for orientation on the sky. It's our own galaxy with large and small Magellanic clouds. But the thing about this diagram is this. Okay, so at this point, oh yeah, sorry, this is another plot from that work, and this is this particular technique of using deep learning. So the idea is, these are 2 other techniques. This is on the data, that's on simulations. It's a projection on the sky, okay? It's a projection on the sky. And we think that this method does better than the other 2. And the idea is you basically teach the computer based on simulations. You show the computer many, many simulations, and then you show the one universe, and it learns from it, from simulations, and it gives you that map. And again, here yellow regions are overdense, and dark red are underdense. Same idea. And this is from a different group in Zurich, that they can even do cosmological studies. So if they only use, these are 2 parameters we like, omega matter, which is the sum of dark matter plus baryonic, which is about 30%. I've said that before. And you can get these results by conventional techniques. Like this one, this is results from cosmic microwave background Planck. And these are some 3 other versions. But what these authors are shown, this is a technique that only makes use of the 2-point correlation function, which I already said is great to start with, but it doesn't convey all the details. Well, what this Swiss group has done is, again, to show the computer many, many simulations, and to say, okay, tell me now what is omega matter, and also this sigma 8. Don't worry about details, it's some measurement of the amplitude of the fluctuations, of how much red and blue you have. So everything is becoming, if you like, computer intensive, throwing at the computer many, many examples. And finally, I think, Joe, I think I should be able to finish this in the lecture in about 5 minutes, if that's okay. I also want to show dynamics, not just to show classification and making maps. So I already mentioned it. You may know that our Milky Way is falling towards Andromeda at about 100 kilometers per second, and one day they will actually collide, and in a few billion years. So don't worry. I hope you can sleep well tonight. It's only a few billion years. from now, but it is going to happen if they're on one line. And the question is, how do you tell the mass? And in fact, that's an equation. I'm closing the circle here. That's an equation you have seen earlier of minus g over r squared plus lambda over 3r. It turns out, while this lambda term is not important, say, in the solar system, it's quite important when you have two galaxies running into each other. And in some earlier papers, we looked at that. And if you put lambda in, you get a different mass for the system. The effect is 13% or so. But what we've done now, and this is with a group, again, at UCL, plus two other colleagues. This is led by my former postdoc. He just moved to Sussex, Pablo Lemos. And what we've done, again, we took simulations with 2 million pairs which look like Milky Way and Andromeda. And there we know everything. That's the nice thing about simulations. We know everything, and we essentially train the computer to learn from those 2 million. If you like, the simplest possible algorithm, you go to the 2 million and you say which is the most similar to Milky Way and Andromeda, and you tell the sum of the masses. But of course, it's much more informative because you can see the overall distribution and not just based on one pair. So this is an AI technique to do that. And we actually, if you like a number to take home, we find that the mass of the sum of Milky Way plus M31, that's what this technique is, the sum, which is the diagonal in this diagram. This is the mass of one, the mass of the other. The diagonal is the sum. It's about 4.6 10 to 12 solar masses with quite large error bars, but still it's a number. And the red are other measurements by other groups of the mass of Andromeda, so-called M31, and the Milky Way, that's the blue one. So we are consistent with that, but obviously we should do more, and I hope you agree with me, it's important to know the mass of our galaxy, just the same way it's important to know the mass of the Earth or of the Sun. So in the last few minutes, and I'll make sure to finish in 5 minutes to allow time for questions, last 5 minutes, I just want to talk about the fourth topic of this talk. We gave the specific example of cosmology. We showed there are lots of surveys, and we show that AI, machine learning, are very important. But obviously, cosmology is not the only game in town. We have lots of data everywhere, all the pictures you take on your mobile phone, all the way to experiments in particle physics, data about COVID, you name it, right? It's just lots and lots of data. So there's a whole area developing of AI machine learning. And we thought, when I say we, it's also the Research Council, division of the Government and Research Council, but also at UCL and in other universities, including in Kent. There's lots of interest in those techniques. And this is a new PhD program, so I thought it might be of interest to you, because fairly soon you'll be finishing your degree. And if you're interested in a PhD, you can, of course, choose, if you're interested in astronomy, particle physics, you can choose, of course, a trajectory which is purely astronomy, okay, or purely particle physics. You can do that, there's no problem. But this is a different trajectory where you come and do your PhD over 4 years, and half a year you spend in a company. And you can see there are different companies which vary from the BBC, The Economist magazine, Transport for London, and so on. That we have about 20 partners. So the students, and there are now 45 of them in 4 cohorts, in this program, which I have the privilege to co-direct, there are 45 students in 4 cohorts. I'm lucky to supervise those 4, Konstantina, Ben, Sunil, and Prab, and on different topics. And they work with me on astronomy, but they also spend 6 months with one of those companies. Ben just finished a placement with ASOS, and Konstantina is about to start a placement with faculty a company called Faculty. And they also, in the first year, do a group project as well with companies. So they end up basically being prepared for a dual career, and I'm sure you can tell the attraction of that. I'm certainly learning from them. They come back to us and teach me new tricks from the industry. So I think it's very interesting. And as a spin-off, we're thinking about the bigger world, and using a Newton Fund, we applied and got funding to extend the project to Jordan. We already planned summer school in London, and we were eagerly waiting to go and visit Petra, but unfortunately COVID got in the way. So we have to do it online. We had the launch event and also a machine learning course. And also it might interest you to know that we have 46 students who are exactly at your stage. They're third and fourth year undergraduates in Jordan, and 62% are female. So I think it's an interesting statistic. So that's it almost. I'll just close in a minute. I think there's no question that cosmology, is many other fields in industry, is going through industrial revolution. There's lots of data in both the spatial domain and time domain, but we have many challenges. Okay, I think it's misleading to tell people, oh, AI will solve all your problems. Okay, it's too immature. Now we also know what can go wrong. If your incomplete training set, if your training set is incomplete, you have to augment the data. Okay, that's what I said. If you don't show the computers dogs, how would it know what dogs are? Should you tell the computer about Newton's law or general relativity? Why not? I mean, there's been a very successful enterprise of learning about this law. So why let the computer to learn Newton's law from scratch? On the other hand, you wish to also discover something new. So who knows? And of course, there's the need to understand and interpret the algorithms. And also, that's something one of my students is working on, benchmarking, upscaling. How do you actually take an algorithm which works successfully for 1,000 objects, maybe 1 million, but now you want to use it for 1 billion? Would it work? Or maybe it might break down. And as we said, whatever happens, I think it's a great way to train PhD students, postdocs beyond academia, and also to open everybody's eyes, from the students to the old professors, about interdisciplinarity, that a lot of the work we do across fields within astronomy and also across technology and medicine and so on are very similar. Are you going to be much wiser? Well, partially depends how good the algorithms are, and also depends if nature is kind enough to reveal something new. So finally, I just want to say that a lot of the work I showed was really done with students and postdocs. I enjoy enormously working with young people who bring fresh ideas. And this is just a thank you from a conference we held in Windsor. Now it's coming to nearly 2 years ago, in the happy days that we could actually all be under one roof and stand, closer than 2 meters from each other. I very much hope, I look forward, this seems to be like a century ago, it's like a dream. I hope very much that very soon, with vaccination and so on, we'll be again in situations like this, and meetings like your wonderful meeting could be held in person. So Joe and the organizers, thanks very much. Thanks for listening, and I'll stop here.
Thank you very much, Professor Lahav. That was a fascinating talk. And
just to ask, would you like to continue sharing this screen, or shall I stop it now?
I think you can stop sharing that now.
Okay, fine, thank you.
No
okay,
problem.
now I can see your faces, right?
Let me just see, do we have any other, if there are any other questions, feel free to put them in the chat quickly while we've still got Professor Lahav here. And if there aren't any, then
yes, there are questions on the chat. I see some questions. Can you see them?
I can, yes. I can.
So would you like to read them? If you could.
Yeah, certainly. I was just seeing if there was few more. So let me see now. So the first question, which came from Alexandru Howe, was what specifically is convolution in ML?
Sorry, I see also another question. Where can I find? Are you reading them by the order they appeared, or? Okay.
Oh, I can do it by the order that they appeared. Well, the first question then in that case is where can we find the translation for Einstein's work on general relativity?
Okay, so there is a website which is an archive which is based in Princeton. So if you presumably Google Princeton Einstein papers, you'll find it. If not, I can send you the actual link to that. Yeah. All right, so that's that question. Yeah, please, next one.
Certainly. The next one again came from Alexandru, which was what is convolution in ML?
Well, so the thing, I don't want to share screen again, so I'll just say that what you can do is take an image, okay? You take an image and you take, if you like, a filter. So it's something which is the same size of the image, but let's say it's got a particular feature in it, a circle or a square, and you multiply one by the other. Okay, that's called convolution. I don't use the exact mathematical definition, but roughly speaking, you have one image, you have another one, you multiply them. So now you have a new image, right? You have a third image, so you keep it. Then, because it gives, well, it gives you some new information now, because it picked up a particular feature, like a circle or a square. And now you take another filter and it has another feature, maybe with a bigger square, you multiply them, you have another number, and so on. So that's called convolution, and that's a trick. Yeah.
Excellent. The question that followed that was, apart from cosmological surveys, what other areas of physics, I presume astrophysics in particular, would you like to see deep learning being used in, potentially detecting surface features on exoplanets and the like?
Yes, so in fact, I know for sure I have colleagues at UCL who use it exactly for that. They analyze surfaces of planets. That's just one example. I mentioned in 2020, 90 papers with deep learning in the title. Okay, so if you go to the archive, the astronomy archive, and put deep learning for the title, you'll find those 90 papers, and it's quite amazing. It's just anything you can imagine in astronomy, from comets to cosmology. So the obvious thing are classification problems, where you don't want to do feature extraction in advance, but there are also various examples where people actually learn about the physics itself, when they're very complicated simulations and they want to pick up some parameters. Yeah, so I encourage you just to look it up, put deep learning astronomy, and you'll find this is 90 papers only in 2020, but of course you have it over the recent years. Yeah, thank you.
The next question relating to the talk was from Professor Mason, who was asking, can you reflect on the limits, if any, of AI in data interpretation and developing new physics? Or what is the human role in this?
Okay, so yeah, so what I was alluding to, beginning about augmented intelligence, is to say that it's not just about, okay, it comes in two ways, so it's quite a deep question, Nigel. I have to decide what direction to take here. But the way I think of it is in two ways, okay? And I've alluded to it, but maybe I'll elaborate a bit. The first one is to say, if we know physics, we know Newton's law, let's find a way to feed it into the process, instead of the poor algorithm having to figure out a very fundamental law of nature, which we know works. So if I take a planetary system, let's say, maybe tell the system that, Newton's law, Kepler's law. On the other hand, what you want also to do is to take, say, data from 1 billion galaxies and analyze it, but you would like to bring it to the expert who has no time to look at 1 billion objects, but maybe might be interested in 10 objects, which are the most peculiar ones. Because maybe of this 1 billion, maybe those 10 are the most interesting ones. Maybe that's where the discovery is. So instead of the poor astronomer having to go to 1 billion in order to finally write a letter to nature, you say, look, the algorithm says, oh, here is a red flag. There's something weird in this object. And then the astronomer would look at the image and say, oh, it's just an artifact. I'm not going to write a paper to nature. Or maybe there is something there which is very new. So that's the way I think about it. It's in any field. I mean, it's someone gave an example. Say someone, an editor of the BBC has very quickly, say, I know, a famous rock star just died, and very quickly they have to find, the right picture to show on the Newsnight. Is the editor going to look through, millions of pictures of that rock star? Or maybe the AI could just, you can narrow it down and say, I would only like pictures from that particular year or of that particular song and things like that. And this way you assist, basically, the human, in this case, the editor, you assist them, and they can then use whatever information for what they need. So that's the way I think about it. But of course, there's more to it, many other examples.
Thank you. I was just going to ask and say, do you think you could ever actually get new physics that way, though?
Well, it may well be that if the, let's say an example, you can devise an algorithm which reports back about deviations from Newton's law. Okay, it will have a tag that says delta is something which is different from zero within errors. And this should, again, it's a red flag. And then you as an astronomer would look and say, is it just some artifacts in the data, or maybe there's new physics? Yeah.
Thank you. Wonderful. Very nice talk.
Excellent. Thank you very much, Professor.
And I see that Alexandra already found the Princeton version. So that's very quick. Very good. I've seen some. Joe, are you moderating other questions?
We've got time for one more question.
One more. Okay. Fine. Please.
Okay, a final question from Adil Mian, which said that I thought overtraining in ML was a result of limited data. So in cases where we have over 100 million galaxies, why is this still a problem?
Well, overtraining is a well-known problem that you overfit. But the problem is if the training set, even if it has 100 million, if it's not representative, if it's not a faithful training set, it could mislead you. Okay, if the proportion of elliptical and spiral galaxies in the training set, even if it's 100 million, is different from the data you're going to use, it could mislead you. Okay, so that's the point about a fair representative data training set. Yeah. I know there's no time for more answers, but just to say, I've noticed questions about this program we have at UCL. So please look up at the UCL website CDT in data intensive science. Unfortunately, we just interviewed for people a new cohort for next year, but some of you may wish to apply in the future as well. And you're also always welcome to write to me, and we can provide more information.
Great, thank you so much. It was wonderful having you join us this weekend, and I hope everyone enjoyed this talk. We're going to take a 15/12 minute break, come back at 5 o'clock for our speed science event, featuring lecturers from the University of Kent telling you about what research they're currently doing. So we'll see you in 10 minutes.
Thank you, Ofer. Take care of
Thank you
yourself.
again.
Pleasure seeing you all.
See you when you're back in the UK and Canterbury.
Yeah. I hopefully, if I manage to get a flight back.
Yeah,
Okay,
take care.
bye.
Bye.
Hey, so I'm going to stop the live stream now.